on page 4-61 of the course pack, and is going to work through an example using the deflection tables that are included on page 4-60 or in the FE manual or in the back of the textbook, deflection tables for the deflection of beams. So this example considers the case of a bookshelf. So the bookshelf is 4 feet wide. The shelves are simply supported on each end, and they are standard 1x12 boards, which in fact are 3/4 of an inch thick and 11 1/4 wide. And we want to estimate the maximum deflection if we've got our new bookshelf stacked up with a whole bunch of calculus books. We'll say that the modulus of wood is 1.5 million psi, and we're going to take our test case of a calculus book that is 1.8 inches thick and weighs 5.5 pounds. So the first thing we need, or one of the first things we need, is the magnitude of the distributed load. And distributed load has to end up in units of weight per length, or force per length, and that is W, and we have 5.5 pounds for every 1.8 inches that we have. So our W ends up being 3.056 pounds per inch. We know that the overall length of the beam is 48 inches. And so the other thing that we need, we know we have E. The other part of our bending stiffness, EI, is the moment of inertia. Rectangular section, BH cubed over 12. Our base is the 11 1/4. The height is the 3/4 of an inch. You cube that, divided by 12, and that ends up with 395 inches to the fourth. Now, what does this loading case look like? We have to go find the appropriate case in our deflection tables. We've got simply supported at both ends, and we've got a uniform distributed load over the whole structure. We're worried about how much the load of books might make the middle of the bookshelf sag. So now we come down here and we look at 4-60 or whatever deflection tables that we have, and we say which one is the most appropriate case. We've got cantilever beams at the bottom, which is not what we're dealing with. We've got our top 3 cases are simply supported, of which this bottom one right here with our -5 times the distributed load, L to the 4th over 384 times the bending stiffness, that's the one we need because we are looking for deflection, not this end slope column. So that's the one that we need. We can get that out of the way. So we know that we need the deflection at L over 2. That's another important piece of this. When you're using the deflection equations, is to remember that these give you deflection for a particular location. For a simply supported beam, that maximum deflection, if the loading is symmetric, is going to be at L over 2 in the middle of the beam. If the loading is not symmetric, as in this case right here, it tells you where it's giving you this max deflection. In this case, it's at location A, which is the distance from the left support to the applied load. In the cantilever cases, on the bottom half of 4-60, all of these have the maximum deflection at the end of the beam, at V sub L. So making sure that you understand where the formula is giving you your max deflection, we can substitute in. And I, as usual, need a little more space. For my calculations. So substituting in what we know, minus 5 times the magnitude of the distributed load times the length of the shelf over 384 times the bending stiffness. This was 1.5 million. This was 0.3955, and that ends up with 0.356 inches. That negative sign, very important, meaning the shelf deflects downward by a little more than 1/3 of an inch. Now, the next segment of this ends up discussing how we can use a composite beam to reinforce the structure, because that 1/3 of an inch, or 0.36 inch, you would definitely see that. And in a lot of cases, the deflection is really a more important design consideration than the actual stress numbers. If you do stress in this beam, you would see that the maximum stress is only about 780 psi, which is really low in the scheme of things, or gives you a very high factor of safety. So to control the deflection, we can be judicious about our material selection, or more efficient about our material selection, if we make a composite beam. Composite beam is where you take more than one material, and in this example we're going to use some aluminum strips to try and support the beam from the bottom and essentially make it a stiffer structure, so the deflection will be less. We do this by considering what we call a transformed section, where basically we use the properties of one to create a ratio so that we end up doing the math as if the whole structure were wood. So we modify the width only of our added supports and multiply it by this ratio of the moduli. We do this because this modulus of elasticity is linear in the width, and if we changed it in the thickness, it would not, the results wouldn't generalize. So we're going to call wood material 1, we're going to call aluminum material 2, and we do this transformed section as if the entire structure is wood. We just make thicker sections of the support beams to account for the fact that we're really going to implement the small aluminum support rails. So our section 1 is our original beam, that's 11 1/4, and our ratio of moduli, again, if wood is material 1, and we know that our support slats are material 2, this is the ratio of aluminum to wood, so that's 10 million over 1.5 million. So our ratio is 6 2/3. So if we were going to use 1/4 inch by 1 inch aluminum strips, we need to do the math as if this is 1 inch times a 6.67 ratio. And also the second one would be 1 inch times a 6.67 is the width. The thickness is still the 1/4 inch of the actual structure that we'll end up using. And so those are our transformed dimensions. We then have to figure out where the centroid of this new composite structure is. So if we locate the centroid of our new composite beam, we know for that we need the areas of each section. We know we need each portion's own centroid location. We take the product of those, and we know that the transformed or the overall centroid of the new section is the sum of those products over the sum of the areas. So we have, for the original beam, area is 11 1/4 by 3/4, 8.4375. Its own distance from our reference datum, and we'll choose our reference datum at the bottom line. So that would be 1/4 inch plus half of the 3/4 of an inch, 0.625. The product of that, 5.2734. And both of the transformed support slats are going to have the same. Our area is 6.67 times 1/4, 1.667. And then from the bottom to its centroid is half of 1/4, 0.125, and that product is 0.2083. Now we multiply these factors by 2 in our sums, so that ends up being 11.771 and 5.6901. Each of these are times 2 and times 2, which ends up in a centroid at just under 1/2 inch from the datum at the bottom of the structure. We can now use that to continue solving the problem. The next thing that we need is the moment of inertia of the composite beam. Moment of inertia I, that's parallel axis theorem. So for the large original beam, we have its moment of inertia plus the parallel axis term. So 1/12 times 11 1/4 times 3/4 cubed plus its area we just found was 8.4375, and the distance between its centroid and the composite centroid we just located There we go. So, the separation distance is 0.625 minus the centroid location of the composite structure that we just found, and figuring that 0.5647 inches to the fourth. Then for the support beams, again, those will be the same. 1/12, again using the transformed geometry, which is 6.667 in the base direction and 1/4 of an inch in the height, and the area of 1.667, and then the distance, separation distance between the centroid of the composite structure and the centroid of the support beam, and that ends up being 0.2228. So summing those for the total transform section moment of inertia is 1.0102 inches to the fourth. Now that we've done all of that, we know that the deflection at mid-beam is the same equation, 5WL to the fourth over 384 EI. And because we've done this transformation to get geometry as if the whole section were in wood, we simply use the modulus of elasticity of wood in the calculation. So minus 5 times the same distributed load, it's our same calculus books, and the length is the same. The support beams run the whole length of the original shelf, 384, 1.5, and 1.0102 inches to the fourth. Now, in terms of moment of inertia, if we scroll back up to the original problem, we see that the original moment of inertia I was 0.3955. So original I of 0.3995. So this addition of the support has made a significant difference in the stiffness of the beam, and so it should be no surprise that we end up with a much smaller deflection. So we've been successful in terms of supporting our shelf so that it doesn't sag. Now, how to consider finding the stresses in the actual wooden shelf. It is, as it ever was, your minus my over I. If we want to look at the stresses in the aluminum section, you need to consider the ratio of the moduli that we used to make the geometric transformation.